So allo or auto, I want to talk about the difference in K-mer spectra of allo-polyploids and auto-polyploids, and want to give you an intuition why these K-mer spectra look different and why they look the way they look. And there are a few ways here for you to get in contact. So I would really like to get your feedback, or if you will use my software, please let me know how it goes, what could be better, what should be different. And if you have questions, of course, get in touch. So as a little outline, we'll start with talking about two types of tetraploids, and you probably are anticipating what these types are going to be. And then I want to try to approach what K-mer spectra are like, starting from population genetics, thinking about Popgen and getting to K-mer spectra. Then I want to talk about fitting parameters to K-mer spectra, and that's using my interactive Tetma app. And then in the end, there's a little summary. And just so you know, at the moment, I am a postdoc here in Edinburgh working on eyebrights. These are parasitic plants, and they have radiators in the UK. And I have studied them on a small island called Faroe. And I'm also a fan of the Julia programming language, but today is not so much about eyebrights, and it's also not about Julia. But just some interesting background, maybe. So, starting with the types of tetraploids, you are probably aware that there can be tetraploids that are auto-tetraploid, where you have 4 sort of homologous genomes represented here by these 4 blue chromosomes. And in auto-tetraploids, you have genetic variation in these genomes that can segregate across these 4 genomes. So if there is meiosis, you get crossing over, and any of these genomes can cross over and exchange information. And then you have the other type, allo-tetraploids, where you have 2 diverged pairs of genomes, and recombination happens more or less only within these pairs. And between the pairs, there's some old homology. These pairs are homologous to each other. And these 2 different types of tetraploids produce different kinds of K-mer spectra. Auto-tetraploid K-mer spectra, if you have looked at a lot of them, you will notice they often have a prominent 4x peak and 1x peak, or I should probably have called them 1n and 4n peak. Whereas if you look at allo-tetraploids, and I reckon the vast majority of tetraploids that people look at are probably allo-tetraploids, you get this prominent 2x peak here, and you might expect that intuitively there are these 2 diverged genomes, so there are probably many K-mers that are present twice, and then they are diverged here, so there's another K-mer that's present twice, and so you get many K-mers here in this 2x or 2n peak. So they have different K-mer spectra. And now you can characterize these K-mer spectra by thinking about blocks of 4 sort of corresponding K-mers. And for instance, if you go at one site in the genome and you compare the 4 corresponding K-mers, they might be all identical. And if that is so, this block of 4 K-mers contributes to the 4x peak. Or you might have a block that is ABBB, so there's 1 allele here and 3 times another allele in the other genomes, and then you get 1 K-mer that contributes to the 1x and 1 that contributes to the 3x peak here. The 3x peak often is not really visible, it's often overlapped by the 4x peak, or there are few K-mers in there, so it doesn't really show. And there are other block types, AABB, which you often find in these allo-tetraploids. And so you can characterize your K-mer spectrum by sort of trying to fit what's the proportion of blocks that have this arrangement and this arrangement and that arrangement. Or you can also try to think about, well, from what I know about population genetics, how often do I expect to see these configurations given a certain level of genetic diversity? And that's what I'm trying to do. And I used for this the blockwise side frequency spectrum machinery. I won't go into detail here, but that's a sort of mathematical or algorithmical framework that was developed by Konrad Lohse, who did his PhD in Edinburgh. He's now a PI here in 2 papers published in Genetics. And this is much more versatile. You can use it to fit demographic histories and look at population data. But it's also very nice to use for K-mer spectrum. So genetic models of K-mer spectra, these block type frequencies that I talked about, they depend on population parameters. And one of them is theta, which is really a fundamental population genetic parameter. Theta, or here the italicized version is a bit more squiggly, corresponds to the genetic diversity in a population. And it is identical to 4 times the effective population size times the mutation rate. And that is not so important. What is important is theta is proportional to the effective population size. The larger the effective population size, the larger will be theta. And in population genetics, people usually think about these idealized populations, panmictic populations that are well mixed, where all of the individuals are of a similar heterozygosity, and it doesn't matter which genomes you look at. So here we have an idealized diploid population, and all these diploids have 2 genomes. And if you look at these 2 genomes here, you can compute what's the heterozygosity. You can also look at this individual and you find the same level of heterozygosity. Or you compare this genome here to this genome here from the other diploid, and you also find the same level of heterozygosity between them. So the genetic information in one individual, the diversity in one individual, reflects the genetic diversity in the whole population. And that's why you can use K-mer spectra to learn about the diversity of a population. So in a diploid, the proportion of K-mer sites that are different between these 2 genomes, that corresponds to theta. So theta is the K-mer heterozygosity in a panmictic population. And now knowing this, you already probably have an intuition about diploid K-mer spectra. The more heterozygous your diploid is, the higher is this 1n peak, because this is where the heterozygous K-mers go. And it is, if it is very little heterozygous, then this heterozygous peak is very low, and the 2n peak is higher. And you can also do that for tetraploids. So we start here with auto-tetraploids. And again, there are these different block types possible. The first one here where you have 4 identical K-mers, and then the second one where you have 3 and 1 that's different, and then 50-50, and then more different K-mers. And using this blockwise site frequency machinery, you can come up with probabilities to observe these configurations that depend on the genetic diversity theta. And then you get these terms here, 1 for each of these configurations. And then you can think, well, I have an auto-tetraploid, a tetraploid, so that has up to 4 peaks in its K-mer spectrum, if you ignore any sort of gene duplication. And you can ask, okay, each of these blocks, where will it contribute to the K-mer spectrum? So for instance, this first one here has 4 identical K-mers, so that will contribute 1 count to this 4x peak here. So we make a little table, these 1 count to the 4x peak, and the other extreme is this, where you have a block with 4 individual different K-mers, that will contribute 4 counts to the 1x peak. And these other configurations here will contribute other counts to peaks. And what you can then do is you just multiply along the lines, and then you sum along the columns. And then you get these terms here, and they all have the same denominator, which is why I called it x. Doesn't matter so much for us what it is now. But from these terms here, you can already tell to some extent what the K-mer spectrum is going to look like. You have this first term here, and that is always going to be larger than the second term, because theta is the genetic diversity, is positive. So 8 theta plus 12 theta squared is always going to be larger than 6 theta plus 6 theta squared. So this first peak here is always going to have more K-mers in it than the second peak. And it's also going to have more K-mers in it than the third peak, because 8 theta is going to be smaller than 8 theta plus something that's positive. We can't tell whether it's taller or not than this last peak here, because we don't know what is theta, is a variable at the moment. So we don't know if this peak is larger or smaller than 6. But you can just put in some dummy data, and then you get your K-mer spectra. So different values of theta, 1, 1/5, and 1/10. You see if theta is low, then the 1x peak or the 1n peak is low, and the 4n peak is higher. If theta is high, you get many heterozygous K-mers. Then this peak here is very high, and the 4n peak is lower. But you see, our prediction is true. The first peak is always taller than the second and the third, even in this low diversity setting here. The first one is higher than the second. And well, here the third peak is sort of overlapped by the fourth peak. But there are more K-mers at this multiplicity than there are K-mers that are truly present in the genome at this 3n multiplicity. So that is thinking about auto-tetraploids. If you have allo-tetraploids with diverged subgenomes, you need an additional parameter that reflects the divergence between these subgenomes. And that is called T, which corresponds to the time that these two here have diverged, since when they've diverged. And this time is measured in generations, and it is scaled by the effective population size. So let's say it's 10,000 generations and the effective population size is 2,000, then T would be 5. And you can then do the same thing. You use this blockwise high frequency machinery, and you come up with some expressions for how many K-mers you expect in each of these peaks. So here now we have an allo-tetraploid with this prominent 2x peak. And these expressions look a bit more complicated. It doesn't matter what they are exactly. What matters is that they all just depend on theta and on T. And if you pick some parameters and stick them in there, you get your K-mer spectrum out of this. So now we know that the K-mer spectrum's shape depends on these parameters theta. And if you have an allo-polyploid, it also depends on T, the divergence time. We can now just go to empirical K-mer spectra and say, well, can we just fit these parameters? What is theta and what is T? And that is what my Tetmer does. And there is a screen capture here where you see what it looks like. It shows you the empirical data here, your K-mer spectrum as circles, as black circles, and that it shows you this red line here, and the red line at the moment corresponds to these parameters here. So here you find theta, and here you find T, and to get a true K-mer spectrum, you also need to add in some other parameters like what's your multiplicity, what's the width of these peaks, because that can vary. So that's a sort of bias parameter. What's the genome size? So you can manually change these values and just play around and see what the K-mer spectrum looks like, given your parameters of choice. Or you can go into the auto-fit mode. And then you can see it snaps into place. At the moment, it's not correct. It's got the 1x peak wrong, but you can adjust the multiplicity range here. And then you can adjust the fitting range, these vertical black lines here, to try to cut off the contamination peak. And then you get your fitted parameters, and you can sort of select them and copy and paste them into your report or wherever you want to have them. And there you get the K-mer multiplicity or K-mer coverage, I say there, your theta, your T estimate, the genome size estimate. By the way, that's not the full genome size, that's the non-repetitive haploid genome size. So that's different to what Kamil's talked about. That does not take the whole K-mer spectrum into account. Yes, and then also an estimate for the divergence between the subgenomes if you have an allo-polyploid. And what I like about this is that it is interactive. So you don't have to submit a job and look what comes out of it, but you can interact with it. And If it does not do a very good job, you can just go back to the manual mode and you can put in parameters yourself and see what does the K-mer spectrum look like. And I think that's quite cool. So now models and reality. I told you that these models, they assume that we have panmictic populations where individuals are sort of well mixed. And if you look at one individual, or if you look at the population, all of them are equally likely to mate and produce offspring with one another. And that's not true in nature. In particular, if you work with plants, you'll find a lot of selfing, where one individual is going to self-fertilize and his offspring are going to be of a lower heterozygosity, for instance. And you sometimes find lineages that sort of self through time, but diverge from one another maybe. You also often get assortative mating when within one population it is not random which individuals mate. And of course there is geographic structure where individuals that are geographically close are more likely to mate than individuals that are further apart. And so our nice panmictic population is a model, but it's different to reality. Often you find that these two genomes here within one diploid are more similar to one another than one genome from this diploid is to one genome of that diploid. And that affects what K-mer spectra look like and what the fits look like. So these here are two allo-tetraploids. It's the same species from the same small island. And you can see one of them has a much taller one-end peak here, and this one has hardly a visible one-end peak here. And that affects the estimate of theta, of the genetic diversity. So our theta estimate does not really well reflect what's the diversity in population. It is off because this individual here is probably the result of selfing, and this individual here is the result of recent outcrossing. So here we will estimate low diversity. Here we will estimate higher diversity. That implies here we would think that the effective population size is quite low. Here you would think that effective population size is quite high. And that then has knock-on effects on this divergence time here, because the divergence time is scaled by the effective population size. So you would expect different values of T divergence between the subgenomes, even though this is the same species and they have the same subgenomes, of course. So that's what you get here in terms of fit. Theta is low, about 2%. Here, theta is estimated much higher, 15%. And that then has a knock-on effect. To get the same level of divergence, T is estimated to 52, while here it is only about 7. And now you can say, well, this is annoying. T, you can't really interpret it as a time. And that's right, that doesn't really work. But what is still very robust is the estimate of the divergence between your subgenomes. So you can multiply theta and T, and then you get an estimate for the divergence between the subgenomes. That's here 0.3. It's not identical here, it's about 0.1, but it's the same ballpark. And so that's the divergence per K-mer between the two subgenomes. And if you divide that by the K-mer length, in this case it was 27, you get an estimate for the divergence per nucleotide between your two subgenomes in this allo-tetraploid. So that's about 5% divergence. I think that's a useful measure to know about. And this is what I just said. And then if you know Tetmer already, there is a new feature here. I've now included tetraploids as well. And in tetraploids, conceptually, you can also imagine there is auto-tetraploids with corresponding genomes and potentially allo-tetraploids with one somehow diverged genome, as you might expect to see if you have cross-ploidy hybridization perhaps. But here's a little animation. This is the auto-tetraploid, and here's the allo-tetraploid with T equals 2. And then during this animation, the values of theta will go up, and you can then compare how these spectra differ. And I can tell you the allo-tetraploid even though theta goes only up to 0.3, it will have a much higher 1n peak. Whereas here in the auto-tetraploid, theta will go up to 0.9, but the 1n peak will always stay lower. Come on. So here you see this goes up really high, even though theta is only 0.3. And here we have 0.9, and the 1n peak is already going down again. So Tetma is not going to tell you it is this ploidy level and this is allo or auto. You have to try out the allo and auto presets and see whether your spectrum fits to them. But I think Tetma is going to help you to decide whether an individual you're looking at is allo-polyploid or auto-polyploid. And then, of course, these K-mer spectra look very different between auto and allo. Yeah, what I just said. And you can fit population parameters to these spectra. And you may have to take them with a pinch of salt if you're working on plants. If you're working on some plants at least, if you're working on outcrossing things, wind-pollinated things, or sea creatures that float around and have large populations, you can probably generalize from what you see in one individual, generalize to the whole population. Ideally, for these analyses to work, that's not Tetma specific, that's a K-mer thing in general. Ideally, for these things to work, you have a clearly visible 1x, 1n peak. And even if there is no 1n peak, it's good to see that there's nothing there. It is tricky to do an analysis if there's much overlap with contamination K-mers. And in allo-polyploids, the genetic structure made by ICRT estimate the divergence time, but subgenome divergence, which is t times theta, is much more robust. And you can get Tetmer from GitHub. The repository is called Shiny K-mers, and here's the publication. And again, some ways to get in touch. And these slides are on my website. So if somebody wants to go back to them, just check out BioEvolgen, and there's a link to these slides. All right.
Thank you, Hannes, for an exciting talk. I think we have still 5 minutes for questions. So I would start with those that are already written. Agnieszka asked if you can use this approach to estimate theta in diploid genomes.
If you, yes, you can. Does it show here? So here you can see what models are available. There's tetraploid, allo and auto, there's diploid, and in diploid you can estimate theta. But you have to remember theta is per K-mer. So if you want to have nucleotide heterozygosity, you need to divide by the length of your K-mers.
Cool. And then we have another question from Simone. Is there an interpretation for T magnitude? Is it somehow convertible to million years ago or percent of divergence?
Yeah, I mean, in theory it is, right? But so people who work on demography, they measure time in generations generally, because and that's how you measure mutation rates as well. You want to know how many mutations happen in the genome per generation. So if you have a good idea, what is your generation time, which might be easy in some plants, for instance, if you work on annuals, and if you have an idea of the mutation rate, then you can convert it into million years. But generally, it will be tricky, and in non-model species, it may be tricky. But I think that's just what you generally find in the field of demography inference. So
the interpretation of T is a number of generations times mutation rate.
Number of generations times effective population size.
And no mutation rate?
No mutation rate, because the mutation rate is already in theta.
Oh, I see.
Yes. Yeah, that's right.
Mhm.
And that's why you can multiply them and get the divergence between the subgenomes.
Cool. I was wondering if for your allo-polyploid, what if the two subgenomes have very different effective population sizes? Imagine that one of the two hybridizing species would have substantially bigger effective population size.
Well, I mean, that's in theory possible. I guess that's what they say is the case in Capsella bursa pastoris, I think. So I did this thinking, well, there's an allo-polyploid and it's probably old now, and it's been an allo-polyploid for a long time. And so I just assume they have a similar effective population size. But you're right. I guess in theory, you could fit an additional parameter there. You could give them different population sizes. But then you make the model more complex and you can fit in all sorts of weird things. And then it becomes hard to discriminate between these different scenarios, allo and auto, for instance. And you can also, for instance, say, I use this allo-polyploid model, but I set my t very low, and then it looks like an auto-polyploid. Yeah, it's always, you always have to ask yourself very hard, is it really useful to add in an additional parameter?
Do I really need this parameter?
in a way, there's relatively little information in these K-mer spectra. And I mean, that's what all of us say, a K-mer spectrum analysis, that is sort of a quick and dirty thing. You can do that before you have an assembly. But if you have an assembly of an allo-polyploid, you will be able to say much more accurately what's going on. Is the effective population size different? Is the nucleotide diversity different in the different subgenomes? So I'm actually not so eager to make it more complicated there.
Sure. Does anybody else have questions? Because I have like a million, but that's I don't want to take the space of everyone. I guess in that case, I would then call for lunch, and Hannes is hanging around, I think. So if you would like to talk more about the different approaches of fitting K-mer models, then you can just find him around. Oh, by the way, Hannes, I thought maybe people would find it really useful if we would explain what's the difference between Tetma and genome scope in a very like broad term. And I was thinking that easiest way to summarize would be that while genome scope is just a combinatoric tool, the Tetmer is like purely population genetics types of base of inference, right? That would be the difference why. That would be the reason why they would be sometimes giving different numbers.
Mm. Yeah, so I don't really know what models are inside genome scope. I mean, I've looked at the code, but get only so far. So the thing, I feel genome scope looks at these configurations here, right? And genome scope somehow figures out how many of each are there. And then genome scope tells you, oh, there's so much of this heterozygosity and so much of that heterozygosity, and that you get percentages for each of these. Mm-hmm. I feel genome scope doesn't really string them together. Genome scope doesn't really know if theta is this, I expect this percentage here and that percentage there and that percentage there.
Yeah, it's not. It's interlinking it with duplications. So it's like using, like assuming the duplications and heterozygosities are randomly overlapping. So I think that's where it's getting like statistical power to fit them all.
So in a way, Tetma doesn't really think about that. Tetma is not aware of duplications. If you have a sort of paralogous peak that is further right from all your peaks, which you commonly see, Tetma will ignore this. Whereas genome scope includes that into the model, into the full model at least, or some of these.
All right, then thank you again, Hannes. It was a great talk. I think